There is a particular kind of silence that falls over a room when someone realizes the ground beneath them is not as solid as they thought. Not the silence of peace, not the silence of rest, but the silence of a mind suddenly suspended between what it believed and what it is beginning to suspect. You have felt that silence before, probably in a smaller context. A relationship, a career, a belief about yourself that turned out to be less certain than you had assumed. But what happens when that silence doesn't fall over a single person, or a single room, or even a single generation? What happens when it begins to descend over the entire enterprise of human understanding? What happens when the people who have dedicated their lives to mapping reality, the physicists, the cosmologists, the mathematicians, the philosophers of science, begin to look at each other across their equations and their telescopes and their particle accelerators and realize, very quietly, that something fundamental is wrong? That is what this is about. Not a minor correction, not a footnote, not the kind of adjustment that science makes routinely, the kind that gets written up in a journal and quietly integrated into existing knowledge. This is about something far deeper, far more unsettling, far more personal than any routine correction. This is about the possibility, supported by real data, by real mathematics, by real experimental results, that the picture of reality we have been building for centuries, the picture we trusted most deeply, the picture that formed the invisible foundation of everything we thought we knew, may be fundamentally incomplete, or fundamentally wrong, or possibly both at the same time. And the worst part, the part that should give you pause right now before we have even begun, is that we do not know which one it is. Before you dismiss that as dramatic overstatement, consider what it feels like to live inside certainty. Consider how it feels to believe that you understand something completely. There is a warmth to it, a stability. When you walk across a room, you do not question whether the floor will hold you. When you watch the sun rise, you do not wonder whether gravity will keep working. When you solve a mathematical equation, you do not worry that the answer might be different tomorrow. These are the kinds of certainties that science gave us. Not metaphorical certainties, not spiritual certainties, but hard, tested mathematical, experimental certainties. And for a long time, those certainties held. They held so well, in fact, that we stopped thinking of them as assumptions. We started thinking of them as facts, as descriptions of reality itself, as the thing underneath everything. And it is precisely that confidence, that deep, earned, celebrated confidence, that is now beginning to tremble. You need to understand how good science was at building that confidence. Because the story of how we came to trust our models of reality is not a story of arrogance or delusion. It is a story of genuine intellectual triumph, of centuries of careful observation and brilliant minds and painstaking experiment. And if you want to feel the full weight of what is now being questioned, you first have to feel the full weight of what was once so certain. You have to go back to the beginning of that confidence, to the moment when human beings first discovered that the universe was not a chaos of mysterious forces, but a system, an ordered, lawful, comprehensible system that followed rules that could be discovered, written down, and used to predict the future. Imagine standing in the late 17th century looking up at the night sky and suddenly understanding that the arc of a cannonball and the orbit of the moon are governed by exactly the same equation. That is what Isaac Newton gave the world. Not just a formula, but a revelation. The revelation that the universe operates according to laws that are universal, laws that do not change from place to place or moment to moment, laws that apply whether you are on Earth or on Jupiter or on some unnamed rock circling a distant star. Before Newton, the heavens were thought to operate according to principles entirely different from those governing the Earth. After Newton, there was only one physics, one set of rules, one underlying logic binding all of matter and all of motion into a single coherent system. The feeling that produced was not just intellectual satisfaction, it was something closer to awe. It was the feeling of a veil being lifted from the face of the universe, and the predictions that followed from Newton's laws were so accurate, so startlingly precise, that confidence in them became almost indistinguishable from certainty. When astronomers noticed irregularities in the orbit of the planet Uranus in the 19th century, they did not assume Newton was wrong. They assumed there must be another planet out there, exerting a gravitational pull they hadn't accounted for. They calculated where that planet should be. They pointed their telescopes, and there it was, Neptune, exactly where the mathematics said it would be. Think about what that moment felt like. You have a theory, you apply it to an anomaly. The theory tells you where to look. You look, and reality obeys. That is not just confirmation. That is a kind of proof that the universe is playing by the rules you have discovered. That is the universe itself telling you that your map and its territory are the same thing. The confidence deepened with every subsequent generation of discovery. In the 19th century, James Clerk Maxwell unified electricity, magnetism, and light into a single elegant framework of equations. 4 equations that describe the behavior of electromagnetic fields, and from those 4 equations, the prediction that light was an electromagnetic wave, traveling at a specific speed that could be calculated from first principles. And when experiments measured the speed of light, they found exactly what Maxwell's equations predicted. Again, reality obedient. Again, the map matching the territory. Again, confidence deepening into something that felt less like a hypothesis and more like knowledge. You could feel, reading the physics of that era, a kind of triumphant momentum, a sense that the work of understanding the universe was not infinite, but merely unfinished, that science was not groping in the dark but advancing steadily toward a complete description of everything. By the end of the 19th century, that confidence had reached a kind of peak. Some physicists of that era spoke openly of the project of physics being nearly complete. The great laws had been discovered. The remaining work was refinement, filling in the decimal places, as it was sometimes said, rather than discovering entirely new continents of knowledge. The universe was understood, at least in its broad outlines. Matter was matter, energy was energy. Space was the fixed stage on which events unfolded. Time was the constant rhythm that measured them, and the laws that governed how things moved and interacted were known and tested and reliable. There was a coherence to it all that felt earned, that felt real, that felt like the truth. And then something happened, something that, when you look back on it now, has the feeling of the first hairline crack appearing in a wall that had seemed perfectly solid. It was not dramatic at first. It did not announce itself as the beginning of a revolution. It appeared, as so many world-altering discoveries do, as a small technical problem, a slight mismatch between theory and observation, the kind of thing that researchers expected to resolve fairly quickly with a minor adjustment to their calculations. The problem was this: when scientists attempted to measure the speed of light relative to the motion of the Earth, they expected to find that the speed varied depending on the direction of measurement, the way the speed of sound varies depending on whether you are moving toward or away from the source. It seemed obvious, it seemed inevitable, but no matter how carefully they designed the experiment, no matter how precisely they made their measurements, the speed of light came out the same in every direction, regardless of the motion of the observer. The universe was not doing what it was supposed to do. The experiment that most famously demonstrated this impossibility was conducted by Albert Michelson and Edward Morley in 1887, and the result was so confounding that it was initially dismissed by many as an experimental error. The assumption, deeply embedded in the Newtonian framework, was that space was a kind of fixed, absolute medium, something like a cosmic ocean through which light traveled and through which the Earth moved, and that by measuring how the speed of light varied with the Earth's motion through this medium, you could detect the Earth's absolute velocity through space. What Michelson and Morley found instead was essentially nothing, no variation, no detectable motion relative to the supposed medium, as if the Earth were standing still, which, given that it orbits the Sun at about 30 kilometers per second, it clearly was not. The measurement was correct. The theory was wrong. Something in the foundations was cracked. It took nearly 2 decades for the full implications of that crack to become clear, and when they did, they came in the form of a young patent clerk in Switzerland who looked at the problem not as a technical glitch to be corrected, but as a signal pointing toward a much deeper truth. Albert Einstein's special theory of relativity, published in 1905, did not patch the crack in the Newtonian wall. It demolished the wall entirely and replaced it with something stranger, something that required you to abandon intuitions that had felt as natural and obvious as breathing. Space, Einstein said, was not fixed. Time was not constant. The passage of time itself, the fundamental rhythm that you feel with every heartbeat, every blink, every breath, was not the same for all observers. Time moved faster for some, slower for others, depending on how fast they were moving and how strong a gravitational field they were in. And the thing that was constant, the thing that stayed the same no matter who measured it, was not time, not space, but the speed of light. Let that settle for a moment, because if you absorb what Einstein was actually saying, not the equations, not the technical formalism, but the raw claim about the nature of reality, it is genuinely disorienting. He was saying that 2 clocks perfectly synchronized when they are at rest together will fall out of sync the moment one of them starts moving. He was saying that the length of a ruler depends on how fast it is traveling. He was saying that the order in which two events occur can appear different to two different observers moving relative to each other. That simultaneity, the most basic feature of time, the sense that this happens before that, is not absolute but relative to the observer's state of motion. The ground of time, which had felt like the most stable thing in the universe, was revealed to be fluid, observer-dependent, woven into the fabric of space in a way that made the two impossible to fully separate. And yet, and this is the part that makes the story both thrilling and deeply unsettling, Einstein's theory worked. It worked spectacularly well. Every prediction it made was confirmed by experiment. Time dilation, the slowing of clocks in motion, was measured directly, first using precise atomic clocks on airplanes, and later confirmed in countless experiments at particle accelerators, where particles moving at near light speed decay more slowly than their stationary counterparts, exactly as relativity predicts. The bending of light by gravity, which Einstein predicted in the General Theory of Relativity published in 1915, was confirmed by observations during a solar eclipse in 1919. The existence of gravitational waves, ripples in the very fabric of spacetime, predicted by the equations of general relativity, was confirmed by the LIGO detector in 2015, a full century after Einstein wrote them down. The theory was strange, yes. It violated intuition, yes. But it was not speculation. It was one of the most thoroughly verified theories in the history of science. So here you have the first major lesson of this story, and it is a lesson that should already be making you slightly uneasy. The fact that a theory works, the fact that it makes accurate predictions, the fact that experiments confirm it, the fact that its equations describe observable reality with extraordinary precision, does not necessarily mean that it describes the complete truth about what reality actually is. Because we now know that Newtonian mechanics worked magnificently for centuries, worked well enough to navigate ships, build bridges, calculate planetary orbits, launch rockets, and yet turned out to be a limiting case, an approximation, a useful model that was accurate only within a certain range of conditions and broke down at high speeds and in strong gravitational fields. And the theory that replaced it, relativity, while being vastly more accurate in those extreme conditions, itself has known breakdowns, situations in which its predictions fail, situations that point toward something deeper, something that neither Newton nor Einstein could fully reach. This is where the story takes a turn that is harder to follow and even harder to accept, because at roughly the same time that Einstein was restructuring our understanding of space and time at the cosmic scale, another revolution was happening at the opposite end of the scale, at the scale of atoms and the particles that make up atoms. And the picture that emerged from that revolution was not just surprising or counterintuitive. It was, by any ordinary standard of what it means for things to make sense, deeply, profoundly, almost offensively strange. The quantum mechanical description of reality is not a small amendment to classical physics. It is an entirely different kind of description, one that operates by different rules, uses different mathematics, and implies things about the nature of reality that even its creators found impossible to fully believe. Consider the double-slit experiment, which is perhaps the simplest and most disturbing demonstration of the quantum strangeness at the heart of physical reality. You have a barrier with two narrow slits cut into it, and you fire tiny particles, electrons, photons, even atoms, at the barrier one at a time. Classical physics tells you what should happen. Each particle should pass through one slit or the other, and hit a detector screen on the other side. Over time, as you fire many particles, you should see two bands on the detector screen, corresponding to the two slits. But that is not what happens. What you see instead is an interference pattern, a series of alternating bright and dark bands, the kind of pattern you get when two waves overlap and either reinforce or cancel each other. The particle is interfering with itself. It is behaving as if it passed through both slits simultaneously, as if it existed as a kind of spread-out wave of probability rather than a localized point of matter. But here is where the strangeness deepens, because when you try to find out which slit the particle actually went through, when you install a detector to observe the process, the interference pattern disappears. The particle stops behaving like a wave and starts behaving like a classical particle, passing through one slit or the other, leaving two bands instead of an interference pattern. The act of observation, the act of gathering information about which path the particle took, changes the outcome of the experiment, not because the detector physically disturbs the particle in some mechanical way, but because the nature of the quantum system is fundamentally altered by being observed. The particle does not have a definite path until that path is in some sense recorded or measured. Before measurement, it exists in a superposition, a combination of all possible states simultaneously. After measurement, it collapses into a single definite state. And the question of what exactly causes that collapse, what happens to all the other possible states, what the wave function of a particle actually is in physical reality, those questions do not have agreed-upon answers among physicists today. Think about what that means. We are talking about the basic building blocks of all matter, the fundamental constituents of every atom in your body, every atom in the chair you are sitting in, every atom in the planet beneath you. And the most successful mathematical theory we have for describing those building blocks, a theory that has passed every experimental test ever devised for it, a theory used in the design of every semiconductor, every laser, every MRI machine. That theory describes these fundamental constituents not as definite things with definite properties, but as probability clouds, as smeared out fields of potential, as entities that only seem to have definite properties when they are observed. What they are doing when no one is looking, whether they are doing anything at all in the conventional sense, is a question the theory deliberately does not answer and may not be capable of answering. Niels Bohr, one of the founding architects of quantum mechanics, reportedly said that anyone who is not shocked by quantum mechanics has not understood it. Richard Feynman, one of the greatest physicists of the 20th century and a man not given to unnecessary drama, said flatly that no one understands quantum mechanics. Not that it is difficult to understand. Difficult things can be understood with enough effort. He meant that there is no coherent picture of physical reality that quantum mechanics is describing, no mental model you can hold in your head that correctly captures what is actually going on at the quantum level. The mathematics works. The predictions are verified. But what it means, what it says about the fundamental nature of reality, that remains genuinely, deeply unresolved. And notice that we now have two enormously successful theories of physical reality: general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which describes the small-scale behavior of matter and energy, that are mutually incompatible, not just in the sense that they make different predictions in some extreme conditions, though they do, but in a more fundamental sense, they rest on incompatible assumptions about the nature of reality itself. General relativity describes a smooth, continuous fabric of space-time, in which every event has a definite location and a definite causal relationship to every other event. Quantum mechanics describes a world of irreducible probability, in which definite locations and definite causal relationships are not fundamental features of reality, but emerge only upon measurement. You cannot combine these two pictures into a single coherent whole. Decades of effort by the most brilliant physicists in the world have not produced a successful theory of quantum gravity, a theory that unifies the quantum description of matter with the relativistic description of space-time. The two pillars of modern physics, the two greatest intellectual achievements of the 20th century, do not fit together. This incompatibility is not a footnote. It is not a problem sitting somewhere on the margins of physics, waiting to be solved as a matter of routine. It is a crack running through the very center of our understanding of reality, because if two of our most successful theories confirmed to extraordinary precision by every experiment ever devised to test them, cannot both be fully correct, then at least one of them, and possibly both, is not describing reality as it actually is, but only as it appears within a limited range of conditions. The map, again, is not the territory. But now we have two maps that contradict each other, and we do not know which parts of each map to trust, or whether either map can be trusted when pushed to its limits. And the limits are real, and they are not hypothetical, and they are not just philosophical curiosities. The breakdown of our theories at their boundaries has direct, measurable consequences. Consider what happens at the center of a black hole. General relativity predicts a singularity, a point of infinite density and infinite space-time curvature, where the equations themselves break down, producing outputs of infinity that are the mathematical equivalent of a theory screaming that it no longer applies. Physicists widely agree that this breakdown is a signal not that nature actually contains infinities, but that general relativity is failing in that extreme regime, that a more complete theory, a quantum theory of gravity, is needed to correctly describe what happens there. But no such theory exists. At the singularity, we are simply lost. The universe is doing something in there, and we have no description, no framework, no language for what it is. Similarly, consider what happened in the first instant after the Big Bang, when the entire observable universe was compressed into a region smaller than an atom, so hot and dense that both quantum mechanics and general relativity are needed simultaneously to describe what was happening, and they cannot be used simultaneously because they are incompatible. The beginning of everything, the origin of all the matter and energy and space and time that you inhabit, is a moment our best theories cannot describe. The most fundamental question about where we come from, not philosophically but physically, is a question our physics cannot answer. The laws we trust to describe reality break down at the very moment reality began. But let's be precise about where we are in this story, because the incompatibility of relativity and quantum mechanics, while deeply troubling, might still be interpreted as a technical problem, a gap to be filled, a bridge to be built, a matter of time and cleverness. What begins to tip this story from a story about an unsolved puzzle into a story about something more profound is the accumulation of anomalies, observations, measurements, data points that do not fit the models we have, that cannot be easily explained by any adjustment to existing theories, that force a more radical reckoning with the possibility that something essential is missing from our picture of reality. Let's start with dark matter, because the story of dark matter is a story that should by itself be enough to shake your confidence in how well we understand the universe. When astronomers in the 20th century began carefully measuring the rotation of galaxies, measuring how fast stars at different distances from the galactic center are orbiting, they expected to find a particular pattern based on the distribution of visible matter in the galaxy, the stars, the gas, the dust. Gravitational physics makes a clear prediction. Stars near the outer edges of the galaxy should orbit more slowly than stars closer to the center, for the same reason that the outer planets of the solar system orbit the sun more slowly than the inner ones. This is basic, well-understood physics. This is physics that has been verified in solar system measurements for centuries. But what they found was completely different. Stars at the outer edges of galaxies do not slow down the way they should. They orbit at roughly the same speed as stars much closer to the center, sometimes even faster. The rotation curves of galaxies are flat where they should be declining. This means there is far more gravitational influence in the outer regions of galaxies than the visible matter can account for. Either gravity behaves differently at galactic scales than it does in our solar system, which would require a fundamental revision of our understanding of gravity, or there is a vast amount of matter in those regions that we cannot see, matter that does not emit or absorb or reflect light, matter that interacts with ordinary matter only through gravity. This invisible substance has been named dark matter, and its existence has been inferred not just from galactic rotation curves, but from dozens of independent lines of evidence. The bending of light by galaxy clusters, the large-scale structure of the universe, the pattern of fluctuations in the cosmic microwave background radiation. The evidence is overwhelming, and yet no one has ever directly detected a single dark matter particle. Decades of experiments, some of the most sensitive instruments ever built, designed specifically to catch dark matter particles. Nothing. It is not there. Or rather, something is there, but we cannot find it, cannot touch it, cannot identify it, cannot explain it. If dark matter is disturbing, dark energy is terrifying, and I do not use that word carelessly. In 1998, two independent teams of astronomers were studying distant supernovae, stellar explosions so bright that they can be seen across billions of light years, as a way of measuring the expansion rate of the universe. The universe has been expanding since the Big Bang. That much was known. What the astronomers expected to find was that this expansion was slowing down over time, pulled back by the gravity of all the matter in the universe. What they found instead was that the expansion was accelerating. The universe is not just expanding, it is expanding faster and faster, driven by some form of energy embedded in the fabric of space itself, an energy that fills empty space uniformly, that does not dilute as the universe expands, that acts as a kind of anti-gravity pushing everything apart with increasing force. This energy has been named dark energy, and it constitutes approximately 68% of the total energy content of the universe. Add dark matter, and you get approximately 27%. Together, dark energy and dark matter account for roughly 95% of the universe. Everything you have ever seen, everything science has ever studied, every star, every planet, every atom measured in every experiment ever performed, all of that ordinary matter makes up approximately 5% of the universe. We live in a universe 95% of whose content we do not understand. We have names for it. We have no idea what it is. Pause there. Just pause and let the weight of that settle. Because it is not a small thing. It is not a minor gap in knowledge. It means that the physics we have spent centuries refining, The physics we tested on planets and stars and particles and light applies in full confidence only to a small fraction of what exists. The universe we modeled so carefully, the universe whose laws we thought we had mapped, is not the whole universe. It is a thin, illuminated sliver floating in a vast darkness that we cannot see, cannot measure, cannot theoretically account for. And this is not a newly discovered problem. Astronomers have known about the dark matter problem since the 1970s and about dark energy since 1998. After decades of effort, we have made essentially no progress in understanding what these things actually are. Now add to this another anomaly, one that has become known as the Hubble tension, and which represents perhaps the most acute crisis in cosmology right now. The Hubble constant is a number that describes how fast the universe is expanding. More precisely, how much faster a distant galaxy is receding from us for every megaparsec of distance between us. Measuring this number precisely has been one of the central goals of cosmology for decades, and we now have two primary methods for measuring it, methods that use entirely different physics, entirely different observations, entirely different instruments. One method involves studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, observed across the entire sky, and using the standard model of cosmology to extrapolate from the early universe to the present. The other method involves measuring distances to nearby galaxies using standard candles, objects of known luminosity, like Cepheid variable stars and Type Ia supernovae. Both methods are well tested, both use rigorous physics, both have been checked and rechecked by independent teams. They give different answers, not slightly different, different enough, at a level of statistical significance high enough that the difference cannot be attributed to measurement error. The two best methods we have for measuring how fast the universe is expanding, methods based on solid, well-established physics, do not agree. Something is wrong with our model. We do not know what. This is not the behavior of a science that has essentially figured out the universe and is just filling in the details. This is the behavior of a science confronting deep structural problems, anomalies that do not yield to minor adjustments, discrepancies that resist every proposed solution, gaps that open wider the more carefully you look. And the thing that should make you lean forward, should make you feel the tension of this moment in the history of human knowledge, is that these problems are not separate, unrelated puzzles. They may be connected. They may be symptoms of a single, deeper failure. A failure not of this model or that model, but of some foundational assumption we have been making about the nature of reality itself. Let's go deeper, because we have only been talking about cosmology, about the large-scale behavior of the universe. The strangeness goes much further in when you look at the quantum world. You have already heard about the double-slit experiment and the collapse of the wave function. But there are deeper paradoxes lurking in quantum mechanics that strike at something even more fundamental than wave-particle duality. There is the problem of quantum entanglement, which Einstein himself famously dismissed as spooky action at a distance, and which has turned out to be not a theoretical quirk, but a real, experimentally verified phenomenon that forces us to rethink what we mean by locality, by the principle that things can only be directly influenced by other things in their immediate vicinity. When two quantum particles are entangled, when they interact in such a way that their quantum states become correlated and then separated by any distance, measuring a property of one particle instantly determines the corresponding property of the other, no matter how far apart they are. Measure the spin of one electron and find it pointing up, and its entangled partner, no matter where it is in the universe, will be found to have spin pointing down when measured. The correlation is perfect. The timing is instantaneous, or so close to instantaneous that any signal mediating it would have to travel faster than light, which relativity forbids. John Bell, an Irish physicist working in the 1960s, devised a mathematical test, now known as Bell's theorem, that could distinguish between a world where these correlations have a local classical explanation and a world where they do not. He proved that if the correlations were due to some local hidden variable, some pre-existing property of the particles that we simply hadn't measured, they would have to satisfy certain mathematical inequalities. In the 1980s, experiments performed by Alain Aspect in France tested these inequalities. The results violated them decisively. More recent experiments, designed to close every conceivable loophole, have confirmed the violation with even greater precision. The correlations are real. They cannot be explained by any local hidden variable theory. The universe is, in a precise and experimentally verified sense, non-local. What does non-locality mean? It means that reality, at the quantum level, is not organized in the way our intuitions tell us it should be. It means that distant parts of the universe can be correlated in ways that cannot be explained by any influence traveling through the space between them. It means that our intuitive picture of the universe as a collection of separate objects interacting by forces that propagate through space and time is not fundamentally correct. It is an approximation, a classical approximation to something stranger and more interconnected. The particles in an entangled pair are not two separate things that happen to be correlated. They are, in some sense, that our language and our intuition struggle to capture a single thing, a single quantum system that is not localized in any particular region of space, even when the particles are separated by vast distances. And here is where the epistemological vertigo truly begins, because what quantum mechanics is forcing you to confront is not just a revision of physics, but a revision of what you mean by an object, by a location, by a cause, by a measurement, by reality itself. The Copenhagen interpretation, the standard teaching textbook version of quantum mechanics, effectively sidesteps the question of what quantum reality is by saying that quantum mechanics is a tool for calculating the probabilities of measurement outcomes, and that asking what is really happening between measurements is not a legitimate scientific question. Shut up and calculate, as the instruction is sometimes summarized. And for practical purposes, this works. You can design transistors and lasers and MRI machines without needing a coherent picture of what particles are doing between observations. But if you actually want to know what is real, if you want to look the universe in the eye and ask what it is made of and how it actually works, the Copenhagen interpretation offers you nothing. It gives you a method without a picture, a calculation without a reality. Other interpretations of quantum mechanics attempt to provide that picture, and each one is more unsettling than the last. The many worlds interpretation, proposed by Hugh Everett in the 1950s, and now taken seriously by a significant number of physicists, says that quantum mechanics should be taken completely literally. When a measurement is made and a particle's wave function appears to collapse into a single definite state, what actually happens is that reality splits. Every possible outcome of the measurement actually occurs, each in a separate branch of a branching, exponentially multiplying multiverse of parallel realities. There is no collapse. There is no randomness. There is only a deterministic wave function describing all of reality simultaneously, branching forever into an incomprehensibly vast tree of diverging worlds. In one branch, the electron spun up. In another, it spun down. In another version of this moment, you made a different choice this morning, and in another version of that, something else entirely. Every quantum event spawns a new branch of reality, and all of those branches exist, fully real, fully complete, utterly inaccessible to each other. Does that seem implausible? Consider the alternative. The alternative, the Copenhagen view, says that quantum mechanics describes only measurement outcomes, not underlying reality. It says that before a particle is observed, questions about its properties are not just unanswered but meaningless. It says that the act of observation does something to reality that ordinary physical processes cannot account for, and it provides no explanation of what that something is or how it works. Both pictures are deeply, deeply strange. And the fact that the most fundamental physical theory ever devised, the most accurate predictive framework in the history of science, admits of no agreed-upon interpretation, no consensus description of what it is actually describing, should strike you as significant. It should make you wonder whether the theory, despite its extraordinary predictive power, is showing you something real or only something useful. Now let's take a step back from the specific theories and look at the larger pattern. What we have is this. We have two great theories of physics, general relativity and quantum mechanics, that cannot be reconciled into a single framework, despite decades of effort by the greatest minds in science. We have a universe whose contents are 95% unknown to us, filled with dark matter and dark energy we cannot identify. We have a measurable disagreement between two methods of determining the universe's expansion rate. We have a quantum mechanical description of reality that no one can agree on the interpretation of, that defies our intuitions about locality, causality, and the nature of objects. We have experimental results that confirm the violation of Bell inequalities, proving that any explanation of quantum correlations must be non-local in a way that contradicts our everyday picture of reality. And we have the haunting, persistent awareness that every theory we have ever trusted has eventually turned out to be an approximation, accurate within its range, but ultimately superseded by something deeper that revealed new strangeness, new questions, new gaps. Why should this time be different? Why should we think that we have now finally reached the bedrock, that the next layer down reveals nothing more surprising than what we have already found? There is a concept in the philosophy of science called the pessimistic meta-induction, and it is one of the most sobering ideas in all of intellectual history. The argument goes like this. Look back at the history of science and you will find that virtually every scientific theory that was once considered our best, most accurate description of reality has since been overturned or significantly revised. Newtonian mechanics was our best theory for over 2 centuries and turned out to be a limiting case of a deeper theory. Classical thermodynamics was our best theory of heat and was replaced by statistical mechanics. The plum pudding model of the atom was our best theory of atomic structure and was replaced by the nuclear model. The static universe model was our best cosmological theory and was replaced by the Big Bang model. In each case, scientists of the era had good reason to believe their theory was basically correct. In each case, they were wrong, not trivially, not in minor details, but in fundamental assumptions about the nature of the thing they were studying. Given this historical pattern, the argument runs, we should expect that our current best theories, general relativity, quantum mechanics, the standard model of particle physics, are also, in some important respects, wrong, or at least deeply incomplete. The pessimistic meta-induction does not say that science makes no progress. It says that the theories at any given stage of science are probably not the final word, and that confidence in them should be tempered by an awareness of how many confident theories came before and turned out to need radical revision. But the unease generated by the theoretical problems is only part of the story. There is another dimension to this crisis that goes beyond physics and cosmology into something more intimate and more deeply unsettling. It has to do with perception, with what your senses are actually showing you, and whether the experience of the world that you take to be reality actually corresponds to what reality is. Because the history of neuroscience and cognitive science has been, in many ways, a parallel history of humbling revision, a gradual revelation that the experience of reality you have lived inside your entire life is not a window onto the world, but a construction built by your brain out of fragmentary, ambiguous, error-prone signals, shaped by evolutionary pressures that had nothing to do with accuracy and everything to do with survival. Consider color. When you look at a ripe tomato and see red, you experience that redness as a property of the tomato, as something out there in the world, independent of you, waiting to be perceived. But what is actually happening is this. The surface of the tomato reflects certain wavelengths of electromagnetic radiation. Those wavelengths enter your eye, strike the cone cells in your retina, trigger electrochemical signals that travel along the optic nerve to the visual cortex, where your brain processes those signals and constructs the experience of redness. The redness is not in the tomato. It is not in the light. It is in your brain, a representation, a code, a symbol that your nervous system uses to track a difference in the world that was relevant to your ancestors' survival. Other animals process the same wavelengths of light and construct entirely different experiences. Mantis shrimps have 16 types of photoreceptors compared to your 3, and their visual experience of the same tomato is something you cannot even begin to imagine. Dogs have fewer color receptors than you do, and see the world in a palette that differs fundamentally from yours. None of these experiences is the right one, the real one, the one that corresponds to what the tomato actually is. They are all representations, all useful maps constructed by nervous systems shaped by evolution, not mirrors held up to reality. And if color is a construction, if the rich, vivid, immediate quality of the colors you see is something your brain adds to the world rather than something it reads off the world, then what else is constructed? What else is a symbol, a representation, an evolved shortcut rather than a direct perception of the thing itself? The answer, when you look carefully at the neuroscience, is nearly everything. The solidity of objects is a construction. At the quantum level, the atoms that make up what feels like a hard surface are mostly empty space, a vast void punctuated by clouds of probability in which electrons might be found. The continuity of your visual field is a construction. Your eyes are in constant rapid motion. Your retina has a blind spot where the optic nerve connects. Your visual cortex fills in the gaps, interpolates, extrapolates, and stitches together a seamless panoramic movie from what is actually a choppy, incomplete, distorted input. The passage of time is a construction. Your brain timestamps events in consciousness after the fact, creating the illusion of a smooth, linear temporal flow from what is actually a complex, asynchronous, and sometimes reordered sequence of neural processes. The neuroscientist Anil Seth has proposed a framework that he calls the controlled hallucination, the idea that what we experience as reality is a kind of prediction machine, a system that is constantly generating a model of the world based on sensory input and prior expectations, and that what we experience as perception is actually that model, not the input itself. The sensory data coming in from the world is used not to construct reality from scratch, but to update and correct a pre-existing model that the brain is already running. When the prediction and the input match, you experience the world as stable and solid and real. When they mismatch, in optical illusions and perceptual disorders, in states of high fever or certain drug experiences, the seams of the construction become visible, and you catch a glimpse of the machinery. You see the brain failing to maintain the illusion of perfect correspondence between its model and the world. And what that glimpse reveals is that the experience of reality you have lived inside your entire life is not given to you, it is built for you, by a system that is optimized not for truth but for adaptive action in an environment it can never directly access. This is not a new philosophical observation. The 18th century philosopher Immanuel Kant argued that the mind imposes structure on experience, that space, time, and causality are not features of things as they are in themselves, but categories of the mind, the cognitive framework through which experience is organized and made intelligible. Things as they are in themselves, what Kant called the Ding an sich, the thing in itself, are in principle inaccessible to us. We can only ever know things as they appear to a mind structured the way ours is structured. What the world is like independently of any perception of it, what it is like when no one is looking, is something about which we can say nothing meaningful. What feels like a radical, counterintuitive philosophical position turns out to have deep support from neuroscience, cognitive science, and quantum mechanics, from three entirely different directions of inquiry, converging on the same deeply unsettling conclusion. The evolutionary biologist Donald Hoffman has pushed this idea further than most, arguing not merely that perception is imperfect, but that it is systematically misleading, that natural selection did not favor organisms whose perceptions were accurate, but organisms whose perceptions were useful, and that accuracy and usefulness can diverge dramatically. He uses a simple thought experiment. Imagine two organisms in competition. One has a perfectly accurate perception of the physical structure of its environment. The other has a simplified, distorted perception, but one that is precisely calibrated to track fitness-relevant information: food, threats, mates, obstacles. Which one survives? Evolution does not select for truth, it selects for survival. And organisms optimized for survival are not optimized for accuracy. They are optimized for speed, efficiency, and fitness-relevant response, which often means simplifying, distorting, and sometimes completely ignoring aspects of the world that are real, but not immediately relevant to staying alive and reproducing. Hoffman's argument, which he calls the interface theory of perception, proposes that our perception of the world is like the desktop interface of a computer, a simplified, user-friendly representation designed not to show you the underlying computational reality of the machine, but to allow you to interact with it effectively. When you drag a file icon to the trash, you are not seeing electrons flowing through circuits. You are seeing a simplified metaphor that allows you to accomplish something without needing to understand the underlying mechanics. In the same way, when you perceive a solid, colored, three-dimensional world of objects in space and time, you are not seeing physical reality as it is. You are seeing a simplified, user-friendly interface designed by evolution to allow you to navigate an environment without needing to understand its deep structure. The world you experience, the world of tables and trees and faces and sunsets, may not resemble physical reality any more than the trash can icon on your screen resembles the physics of semiconductor memory. Now hold this thought alongside quantum mechanics. Hold it alongside the fact that quantum mechanics also tells you that the apparently solid, definite, localized world of objects that you perceive is not what reality looks like at its most fundamental level, that at the quantum level, there are no definite locations, no definite properties, no sharp boundaries between separate objects, only probability amplitudes and entanglement and wave functions that spread across space in non-local, indeterminate patterns. The phenomenal world, the world you perceive, looks absolutely nothing like the quantum world our best physics describes. Neuroscience tells you that the phenomenal world is a construction of your brain. Quantum mechanics tells you that the physical world at its most fundamental level is nothing like the phenomenal world you experience. Put these two things together and the question becomes very sharp. Is there any sense in which the reality you perceive, the reality you feel you inhabit, the reality you navigate and interact with and build your life around, Is there any sense in which that bears any direct, reliable correspondence to what is actually out there? You might be tempted to save yourself from this vertiginous conclusion by pointing to science itself as the corrective. Science is the process by which we systematically correct our misperceptions, by which we build instruments that extend our senses and mathematics that transcends our intuitions and protocols that filter out our biases. And that is true, and it is important, and science has genuinely succeeded in revealing aspects of reality that raw perception could never reach. But science is also done by human minds, processed through human cognitive architectures, interpreted through human conceptual frameworks, and limited by the instruments and mathematics that human minds have been able to conceive and construct. We can correct for many biases and many perceptual limitations, but we cannot step outside our cognitive architecture entirely. We cannot know what we are missing because we are missing it. The blind spots we cannot see are, by definition, the ones we cannot account for. This is sometimes called the hard problem of knowledge, the problem that any attempt to examine the tools of knowledge is itself made using those same tools, so that a full and unbiased assessment of their limitations is in principle impossible. We are trapped inside our own cognitive framework the way you are trapped inside your own skull. You cannot get outside it to check whether what it tells you corresponds to what is really there. You can extend it, refine it, cross-check it against itself, but you cannot escape it. And if that framework has systematic blind spots, if there are features of reality that our cognitive architecture is simply not built to perceive, represent, or understand, then those features will remain permanently inaccessible to us, not because we haven't looked hard enough, but because we cannot look at all, because the looking apparatus itself is the limitation. Physics has begun, in its most speculative but increasingly serious theoretical work, to bump up against exactly this kind of wall. The problem of consciousness is perhaps the most dramatic example. Consciousness, the fact that there is something it is like to be you, the fact that your experience of the color red is not just a neural computation, but a felt quality, a what it is like, is perhaps the most fundamental fact about your existence, and it is completely unexplained by current science. Not poorly explained, not partially explained, completely unexplained. We have good and growing knowledge of the neural correlates of consciousness. We know which brain regions and which patterns of neural activity tend to be associated with specific conscious experiences. But we have no theory, not even the beginning of a theory, of why any physical process should be accompanied by subjective experience at all. Why isn't it all just computation in the dark? Why is there something it is like to be a brain processing visual information rather than just information processing with no experiential quality? This is what the philosopher David Chalmers named the hard problem of consciousness, and it remains, after decades of intense philosophical and scientific attention, completely unsolved. Some philosophers and scientists have responded to the hard problem by proposing panpsychism, the idea that consciousness, or some proto-experiential quality, is a fundamental feature of reality, present in some form at every level of the physical world, not something that mysteriously emerges from non-conscious matter at a certain level of complexity, but something that is woven into the fabric of the universe from the beginning. This is not mysticism. It is a serious philosophical position held by serious thinkers, motivated by the genuine difficulty of explaining how consciousness could arise from entirely non-conscious physical processes. It is also, of course, deeply strange. It implies that the universe is, in some fundamental sense, experiential, that the electrons and quarks and fields that make up physical reality are not purely mechanical, purely objective, purely exterior things, but have some interior experiential dimension, however primitive, however unlike our own experience. And if that is true, then the picture of reality that physics has been building, a picture of purely external, objective, non-experiential physical processes, is radically incomplete. It has been describing the outside of things without any recognition that there might be an inside. The theoretical physicist John Archibald Wheeler, who worked with both Einstein and Bohr and spent decades thinking about the foundations of quantum mechanics, eventually arrived at a radical proposal that he encapsulated in the phrase "it from bit," the idea that physical reality, at its most fundamental level, is not made of matter or energy or fields, but of information, of yes or no answers to binary questions posed by measurement. In Wheeler's view, the universe is not a collection of things that exist independently of being observed, but a self-referential system in which the asking of questions, the act of observation and measurement, is what brings physical reality into being. Every particle, every field, every structure in the universe has its ultimate basis in information, in the act of being registered, recorded, distinguished. Existence itself is, on this view, information all the way down. This might sound like philosophy rather than physics, but the idea has been taken up in serious theoretical work. The holographic principle, arising from work on string theory and black hole thermodynamics, suggests that the information content of a region of space is proportional not to its volume, but to the area of its boundary, that a three-dimensional region of space can be fully described by information encoded on a two-dimensional surface surrounding it. The implication, taken seriously by many theoretical physicists, is that the three-dimensional space you inhabit may be, in a deep mathematical sense, a projection of a lower dimensional reality, that what you experience as three-dimensional space, as depth, as the spatial volume in which you move and live, may be an emergent feature, a large-scale appearance, rather than a fundamental property of the universe. This is where the language of physics begins to sound like science fiction, but it is important to understand that these are not casual speculations. They are serious theoretical proposals motivated by rigorous mathematics, by the behavior of quantum information near black holes, by attempts to reconcile quantum mechanics with gravity. The holographic principle, in its technical form, is one of the most important and widely studied ideas in theoretical physics of the last 30 years. Supported by a vast body of mathematical evidence, even if its ultimate physical interpretation remains deeply uncertain, and what it suggests, that the dimensionality of space, the three-dimensional character of the world you move through, may be an emergent phenomenon rather than a fundamental one, is perhaps the most destabilizing claim that physics has yet produced. Because if space itself is not fundamental, if the three dimensions of your experience are a kind of projection, a large-scale appearance arising from a lower dimensional substrate, then what you have taken to be the most basic feature of your existence, the fact that you are here in this place at this location in space, is not fundamental. It is emergent. It is, in the deepest possible sense, an appearance. And now consider time. Time is so fundamental to your experience that it barely registers as an assumption. It just is. It flows. It carries you forward from moment to moment with an immediacy and a directness that makes it feel more real than almost anything else. But the physics of time is deeply puzzling in ways that most people never encounter. The fundamental equations of physics, both classical and quantum, are time-symmetric. They work equally well run forward or backward in time. There is nothing in the basic laws of physics that distinguishes the past from the future, that explains why time flows in one direction rather than another. The arrow of time, the felt direction of temporal flow, the fact that you remember the past but not the future, the fact that broken eggs do not reassemble themselves, the fact that heat flows from hot to cold rather than from cold to hot, is not built into the fundamental laws but arises from a statistical property of large systems, the tendency of entropy, of disorder, to increase in one temporal direction. But this thermodynamic arrow of time depends on a special initial condition, a very low entropy starting point for the universe, whose origin is itself unexplained. More troubling still, the equations of general relativity, the theory that governs the large-scale structure of space-time, treat time not as something that flows, but as a dimension of a four-dimensional space-time manifold, laid out all at once, with all of its moments existing simultaneously in what physicists sometimes call the block universe. In the block universe picture, the past, present, and future all exist equally and simultaneously. The universe is a four-dimensional structure in which all events are fixed and real, and the sensation of time flowing is a feature of consciousness, not a feature of physical reality. The physicist and philosopher Hermann Weyl put it starkly: the objective world simply is. It does not happen. Only to the gaze of my consciousness, crawling upward along the world line of my body, does a section of this world come to life as a fleeting image in space, which continuously changes in time. If this picture is correct, and it is the picture implied by the mathematics of general relativity, then the flow of time you feel with every breath and every heartbeat, the most immediate and personal feature of your existence, is a kind of illusion. Not a metaphorical illusion, not a poetic illusion, but a genuine illusion, a feature of experience that does not correspond to anything in physical reality. There is a physicist named Julian Barber who has spent his career arguing that time does not exist at all in any fundamental sense, that the appearance of time, of change, of motion, emerges from a static, timeless structure of configurations, of arrangements of things with no preferred direction, no built-in flow, no objective present moment. In Barber's framework, what we call the present moment is simply a configuration of the universe that contains within it records, memories, traces, structures that seem to point to a past. There is no actual past. There is only a present that looks as if it has a past because it contains records. This is a position that sounds, when first encountered, like a provocation, like philosophical game-playing rather than serious physics. But it is taken seriously by serious people, and the mathematics behind it is rigorous, and the problem it is trying to solve, the problem of reconciling the time-symmetric laws of fundamental physics with the experienced directionality of time, is a genuine and deep problem that has no universally accepted solution. So here we are, and I want you to feel where we have arrived in this story. We began with the triumph of Newtonian physics, a universe governed by clear universal laws, comprehensible and predictable. We followed the crack that appeared in that picture with the Michelson-Morley experiment, and we watched it widen into the revolutions of relativity and quantum mechanics. We noted that these two revolutions, for all their predictive success, are mutually incompatible and together cover only 5% of the universe's contents. We saw that the remaining 95%, dark matter and dark energy, is completely uncharacterized, that the expansion rate of the universe is being measured by two methods that disagree, that quantum entanglement violates our intuitions about locality in ways that have been experimentally confirmed. We trace the implications of neuroscience and cognitive science, that the world you experience is not a direct perception of reality, but a construction of your brain, optimized for survival rather than accuracy, with systematic distortions and limitations that cannot be fully corrected by introspection. And we have now reached the point where the theoretical frontiers of physics suggest that space itself may be emergent rather than fundamental, that time may not flow in any objective sense, that information rather than matter may be the most fundamental substrate of reality. At this point in the story, a particular kind of intellectual vertigo begins to set in, not the vertigo of being confused about a technical problem, but the vertigo of realizing that the very concepts you have been using to make sense of the problem may themselves be part of the problem, because the concepts of space, time, matter, causality, observation, existence, these are the conceptual building blocks out of which every thought, every question, every theory is constructed. They are so fundamental to human cognition that questioning them is not like questioning an assumption within a framework. It is like questioning the framework itself. And when the framework is questioned, when the very categories of thought become uncertain, something very strange happens to thinking. It starts to feel like trying to use a ruler to measure the ruler. The tool of inquiry is made of the same material as the thing being inquired into. Physicists who work on the foundations of quantum gravity, on the attempt to build a theory that unifies quantum mechanics with general relativity, often report this vertiginous quality in their work. The dominant approaches, string theory, loop quantum gravity, causal dynamical triangulations, and others, all suggest in different ways that space and time at the Planck scale, at distances of about 10 to the minus 35 meters, do not have the smooth, continuous character they appear to have at the scales we can observe. At that scale, space-time may be discrete, made up of fundamental units that have no further structure, that cannot be subdivided, that represent the actual granularity of reality, the way pixels represent the granularity of a digital image. Or space-time may be a network of quantum entanglement, with spatial distance being a measure of entanglement strength between regions, so that what we call space is actually a pattern of quantum correlations, and the geometry of the universe is a large-scale emergent property of underlying quantum information structure. In either case, the implication is the same. The smooth, continuous, three-dimensional space in which you experience yourself as existing, the space in which you reach out your hand and feel it encounter another object across a distance, is not a fundamental feature of reality. It is an emergent feature, a large-scale pattern, a kind of collective behavior of underlying quantum processes that individually have no spatial character at all. The distance between your hand and the object it reaches toward is not a primitive fact about the universe. It is a derived fact, an emergent property, a measure of something more fundamental that is not, itself, spatial. If this is correct, then the very act of locating yourself in space and the most immediate and foundational sense of being somewhere, of being here, is pointing to something real, but describing it in the wrong language. The language of space is an approximation to something for which we do not yet have a language. And this is where the story intersects with something that, a few decades ago, would have been considered firmly in the territory of speculative philosophy rather than serious physics. the simulation hypothesis. The idea, in its most basic form, is that reality as we experience it might be a computational simulation, a vast information processing system running on some substrate entirely unlike anything we can observe from within it, producing as its output the appearance of a physical universe, with consistent laws and structures and inhabitants who experience it as real. The philosopher Nick Bostrom gave this idea its most rigorous contemporary formulation, arguing that at least one of three propositions must be true. Either virtually all civilizations capable of running detailed simulations of their own history go extinct before reaching the technological maturity to do so, or virtually all technologically mature civilizations choose not to run such simulations, or we are almost certainly living in a computer simulation. His argument is probabilistic. If simulated civilizations vastly outnumber non-simulated ones in the universe, then in the absence of specific evidence either way, the probability that any given civilization is the real one is very low. What is interesting from a physics perspective is not the simulation hypothesis itself, but the way it resonates with ideas that are being developed from entirely within mainstream theoretical physics. The holographic principle, as mentioned earlier, suggests that the universe's information content is encoded on a boundary, and that the three-dimensional interior we experience is, in some sense, a projection. The emergence of space-time from quantum information, as explored in the AD-CFT correspondence and related frameworks in string theory, suggests that the universe we experience is in some sense an output of a more fundamental computational process. The discreteness of space-time at the Planck scale suggests a kind of pixelation of reality, a minimum resolution below which structure dissolves. None of these ideas are the simulation hypothesis, and most physicists who work on them would not use that language. But they all point in the same direction. The reality we experience may be a high-level description, an emergent representation, of something more fundamental that does not itself look like reality as we know it. And there is a specific physical observation that has been used to argue for the possibility of a simulated reality in a more direct way. It concerns the behavior of cosmic rays at very high energies. In 2012, physicists at the University of Washington noticed that certain constraints that would arise in a simulated universe, specifically constraints arising from the discreteness of the underlying computational lattice, might leave observable signatures in the spectrum of high-energy cosmic rays. The observation of a cutoff in cosmic ray energies known as the Greisen-Zatsepin-Kuzmin limit, while explainable by other means, has characteristics that are consistent with what you would expect from a discrete underlying computational structure. This is not conclusive evidence, it is not even strong evidence. But the fact that a question that was purely philosophical 10 years ago has been translated into a potentially testable physical prediction is itself remarkable. It means the hypothesis has been brought into the domain of science, and science must now at least try to address it. But let's not lose ourselves in the most speculative territory without first acknowledging how strange and unsettling the more firmly established physics already is. Because the strangeness of quantum mechanics, the problems of dark matter and dark energy, the incompatibility of general relativity and quantum mechanics, the Hubble tension, these are not speculative. These are hard, confirmed, persistent problems that the very best physics currently available cannot resolve. And the response of the scientific community to these problems is itself instructive, because it is not uniform, not calm, not confident. It is a community under genuine intellectual stress, producing a proliferating array of proposed solutions that, in their diversity and mutual incompatibility, reveal how deep the uncertainty goes. Consider the attempts to solve the dark matter problem. Over the decades, physicists have proposed dozens of candidates for what dark matter might be. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and numerous more exotic possibilities. Each of these candidates has been searched for extensively, with increasingly sensitive instruments, and none has been found. The WIMP miracle, the theoretical argument that particles with the mass and interaction strength expected of WIMPs would naturally produce the observed abundance of dark matter, was one of the most compelling arguments in particle physics for decades. It motivated enormous experimental programs, massive underground detectors, accelerator searches, satellite observations, and the WIMPs have simply not appeared. Not at the masses and cross-sections that the simplest models predicted. Not at any of the masses and cross-sections that subsequent more elaborate models have predicted. The most natural and theoretically well-motivated candidate for dark matter has been ruled out, not once, but repeatedly, at successively more sensitive levels. Something is out there. We do not know what it is. The same story plays out in the search for physics beyond the standard model of particle physics. The standard model is perhaps the most precisely tested theory in the history of science. It predicts the properties of subatomic particles with extraordinary accuracy, in some cases to 10 or more decimal places. But physicists have always expected that it would break down at high enough energies, revealing new particles and new interactions that would point toward a more complete theory. When the Large Hadron Collider at CERN began operating, there was enormous excitement and expectation. It was widely believed that the higher energies it could probe would reveal supersymmetric particles, extra dimensions of space, or other new physics that would begin to resolve the open questions. The LHC discovered the Higgs boson, completing the standard model. But beyond the Higgs, nothing. No supersymmetric particles, no extra dimensions, no new forces. Just a standard model that keeps confirming itself at every energy the LHC can probe, with no hints of what lies beyond. The accelerator built to find the new physics beyond the standard model has, so far, found only the standard model. This is not failure in the ordinary sense. The absence of a signal is also a result, and it is a result that constrains theories. But the psychological effect on the physics community has been real and significant. Theoretical frameworks that were once considered almost certain to be correct, supersymmetry in particular, which has been the dominant framework for extensions of the standard model for decades, with thousands of papers written and entire careers built on it, have been severely constrained, if not effectively ruled out in their most natural forms. And without the guidance of experimental results pointing toward new physics, theoretical physics has fragmented into a proliferating landscape of competing frameworks, each with its own internal logic and its own mathematical beauty, none with decisive experimental support. String theory, loop quantum gravity, asymptotic safety, causal set theory, these are the major candidates for a theory of quantum gravity, and after decades of development, not one of them has produced a clear, unique, testable prediction that would allow experiment to adjudicate between them. The philosopher of science Richard Dawid has written about what he calls non-empirical theory assessment, the idea that in a situation where experimental testing is impossible or practically infeasible, physicists evaluate theories based on criteria like mathematical consistency, internal coherence, the ability to naturally explain known phenomena, and the degree to which a theory unexpectedly unifies or explains things it was not originally designed to explain. This is a legitimate form of theoretical evaluation, and it has always played a role in physics. But when it becomes the primary form of evaluation, when experimental falsification becomes impossible or decades distant, the distinction between physics and mathematics begins to blur, and the question of whether the theories are describing reality or just exploring the space of mathematical possibility becomes genuinely difficult to answer. String theory has been criticized on exactly these grounds. It is mathematically vast, internally consistent, and has produced genuine mathematical insights, but it makes no unique, testable predictions, and it accommodates such a huge range of possible physical scenarios that it is unclear how experiment could ever conclusively rule it out. Some physicists have responded to this crisis by proposing that we fundamentally reconsider what we mean by a physical theory, what we require of it, what it means to explain something. Lee Smolin, in his book, The Trouble with Physics, argued that the field has lost its way, that it has allowed mathematical elegance to substitute for physical understanding, that it has become too comfortable with untestable theories, and that a radical return to first principles and experimental guidance is needed. Others, like Leonard Susskind, have embraced the landscape of string theory, the fact that the theory permits an enormous number of possible universes with different physical laws, and combined it with the anthropic principle, arguing that we live in the universe we do, because it is one of the rare ones compatible with the existence of observers, and that seeking a unique theoretical explanation of our universe's parameters is a misguided project. This is a deeply uncomfortable position, because it effectively says that some of the most fundamental questions about why our universe has the properties it does may have no deeper theoretical answer, only an anthropic one. If correct, some of the deepest questions in physics are not waiting to be answered by a better theory. They may simply not have answers of the kind we hoped for. But of all the strange and unsettling developments in physics of the last decade, there is one that deserves particular attention because it strikes at something so fundamental that even physicists who are comfortable with all the strangeness of quantum mechanics and all the mysteries of dark energy tend to pause when confronted with it. It is the problem of the measurement basis, or more broadly, the problem of quantum decoherence and the classical world. Here is the question: why, if the universe is fundamentally quantum mechanical, do we live in a world that looks classical? Why are the objects around you definite, localized, and not in superpositions of multiple states? Why does the quantum indeterminacy that governs particles not propagate upward into the everyday world of tables and chairs and human beings? The standard answer, decoherence, is that quantum superpositions become undetectable at large scales because macroscopic objects interact with enormous numbers of environmental particles, and these interactions entangle the object with its environment in such a way that the quantum interference effects that would reveal the superposition effectively vanish from any practical observation. The object still exists in a superposition in the mathematical sense, but the superposition becomes, for all practical purposes, indistinguishable from a classical mixture of definite states. This is a good answer, and it explains a great deal, but it does not fully solve the measurement problem. It explains why we cannot observe quantum superpositions at macroscopic scales, but it does not explain why measurement produces a definite outcome at all, why the wave function appears to collapse to one particular state rather than continuing to evolve as a superposition. Decoherence replaces a superposition with a mixed state, but it does not produce a single definite outcome. For that, you still need either a collapse postulate that is not derived from Schrödinger's equation, or the many worlds proliferation of branches, or some other additional interpretational machinery. The measurement problem is not solved, it is managed, and there is something deeper lurking here, something that becomes visible when you push the question far enough. Quantum mechanics, as it is currently formulated, is a theory about the outcomes of measurements. The wave function evolves according to Schrödinger's equation in the absence of measurement, and collapses according to the Born rule upon measurement. But what is a measurement? This turns out to be extraordinarily difficult to define precisely. In practice, physicists know a measurement when they see one. It involves a macroscopic apparatus, an interaction that amplifies a quantum signal to classical scale, a record that persists in time. But none of these criteria is sharp. None of them is derivable from the fundamental quantum equations, and none of them specifies exactly when quantum evolution stops and collapse begins. The boundary between quantum and classical, between the microscopic and the macroscopic, between the system and the observer, is not defined within the theory. It is imported from outside the theory, from our common sense experience of a classical world. Quantum mechanics, the most fundamental physical theory we have, depends for its application on the existence of classical observers using classical measuring apparatus, the very things it should, if complete, be able to derive from its own first principles. This circularity, the fact that quantum mechanics presupposes the classical world it is supposed to explain, is one of the most serious conceptual problems in the foundations of physics. It suggests that quantum mechanics, for all its extraordinary success, is not a complete, self-contained theory of reality, but a calculational framework that is embedded in and dependent on a larger context it cannot itself describe. And this, again, raises the possibility that what we are missing is not a refinement of quantum mechanics, but something much more fundamental, a new framework in which quantum mechanics and classical physics both emerge as limiting cases of a more complete description, the way Newtonian mechanics emerges as a limiting case of relativity. What that more complete description would look like, what concepts it would use, what it would say about the nature of reality, we do not know. We do not have a single well-defined proposal that has succeeded in resolving the measurement problem in a completely satisfying way. Let's bring all of this back to something personal, something immediate, because the abstract has been building long enough, and it is time to feel what it means. You are sitting somewhere right now, in a chair, on a couch, in a bed, wherever you are, and the experience of that place feels utterly solid, utterly real, utterly undeniable. The light you see has color. The surface beneath you has texture and resistance. The air around you has temperature. The thoughts flowing through your mind feel like your own, felt from the inside, immediate and personal. This is your reality. It is the only reality you have ever directly encountered. And everything we have been discussing, the incompleteness of our physical theories, the mystery of dark matter and dark energy, the non-locality of quantum entanglement, the constructed nature of perception, the possible emergence of space and time from something more fundamental. All of it converges on a single deeply unsettling question. Is this experience, this immediate, vivid, personal reality that you cannot doubt because you are inside it, does it correspond to what the universe actually is? And the honest answer, if you take all of the evidence seriously, is we do not know. Not in the sense of I haven't gotten to it yet. Not in the sense of it's a hard problem, but we're making progress. In the sense of we have been looking as carefully and as rigorously as we can, with the best instruments and the best mathematics human beings have ever produced, for decades and centuries, and we have found extraordinary things. And among the things we have found is the persistent, deepening suggestion that the experience of reality and the structure of reality do not coincide, that the map we carry in our minds, and the map our science has been building, is a map of the appearance of something we cannot directly access, not the thing itself. Here is a concrete way to feel this. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is a sphere of about 93 billion light-years in diameter. Within that sphere, there are an estimated 2 trillion galaxies, each containing hundreds of billions of stars, most of those stars orbited by planets, and the universe has been in existence for nearly 14 billion years. The scale of what exists is so far beyond ordinary human comprehension that no analogy can adequately capture it. And yet of all of that, of those 2 trillion galaxies and hundreds of billions of stars each, we can directly observe only the light that has reached our instruments, light that is in many cases billions of years old, showing us not what those galaxies are now, but what they were when the light left them, a snapshot of a past that may bear no resemblance to the present state of those systems. We are looking at the universe not as it is, but as it was, and the further away we look, the further back in time we see, until at the very edge of the observable universe, we are looking at a time before galaxies even existed, a time when the universe was a hot, dense, nearly featureless plasma of particles and radiation. And beyond that edge, beyond the observable horizon, there is more. We do not know how much more, possibly infinitely more, that we cannot see, cannot measure, cannot in any way access, because the light from those regions has not had time to reach us. The universe we can study is a tiny bubble inside something vastly larger that we can say nothing about. And even within our observable bubble, even within the 5% of the universe's contents that consists of ordinary matter that we can detect and study, there are structures and phenomena that remain deeply mysterious. The origin of life, the question of how self-replicating, information processing, metabolizing systems first arose from non-living chemistry, has no agreed-upon scientific explanation. The nature of consciousness, why any physical system should have subjective experience, has no agreed-upon scientific explanation. The origin of the universe itself, what caused the Big Bang, what existed before it, whether the concept of before even applies, has no agreed-upon scientific explanation. These are not peripheral questions. They are the most fundamental questions about the nature of existence, and they remain open. Some scientists respond to this catalog of mysteries by invoking the asymptotic progress of science, the idea that while we have not yet answered these questions, we are on a trajectory toward answering them, that the history of science is a history of mysteries gradually yielding to investigation, and that patience and continued effort will eventually close the remaining gaps. This is a reasonable and in many ways admirable response, and it has been vindicated many times in the history of science. Mysteries that once seemed permanently intractable, the origin of the chemical elements, the mechanism of heredity, the cause of infectious disease, have yielded to scientific investigation, often through breakthroughs that seem to come from nowhere. It would be premature to declare any mystery permanently beyond scientific reach. But there is a difference between mysteries that yield to more of the same kind of investigation and mysteries that may require a fundamentally different kind of framework to address. And some of the mysteries we have been discussing, the measurement problem in quantum mechanics, the hard problem of consciousness, the incompatibility of general relativity in quantum mechanics, the nature of dark energy, have the character not of problems awaiting more data, but of problems that may require a conceptual revolution, a new way of thinking about the nature of reality that goes beyond current frameworks in ways we cannot currently anticipate. The history of science includes not only the gradual resolution of mysteries, but also the revolutionary moments when the entire conceptual framework had to be abandoned and rebuilt, when the questions themselves had to be replaced, not just the answers. We may be living in the early stages of such a moment. There is a particular quality to the historical moments just before a major scientific revolution that is worth noticing. They are characterized not by the absence of knowledge, but by an excess of it, by the accumulation of anomalies, the proliferation of competing frameworks, the deepening sense that the existing paradigm cannot accommodate all the things that have been discovered, combined with a complete absence of consensus about what the new paradigm should be. Thomas Kuhn, in his landmark work, The Structure of Scientific Revolutions, described this as the crisis phase that precedes a paradigm shift, a period of intellectual ferment in which the old framework is clearly failing, but the new one has not yet crystallized. Looking at the current state of theoretical physics, the multiplying anomalies, the incompatible theories, the failed experimental searches, the foundational debates that have been ongoing for a century without resolution, it is difficult not to notice that it has exactly this character. The crisis is not coming. It is already here. What makes this crisis particularly profound, what gives it a weight that goes beyond the merely technical, is that the questions being forced open are not just questions about the behavior of particles or the dynamics of space-time. They are questions about the nature of existence itself, about what it means for something to be real, about the relationship between mind and world, about whether the universe has a structure that is accessible to human understanding, or whether it contains depths that are permanently beyond our cognitive reach. These are questions that science and philosophy share, questions that have been debated for millennia, questions that seemed, for a brief and perhaps illusory period in the late 19th century, to be on the verge of final resolution. That illusion is now fully dissolved. The questions are open again, and they are open in a way that is informed by all the physics and mathematics and neuroscience and philosophy that has been done since, which means they are open in a richer, more precise, more urgent way than they have ever been before. Imagine standing at the edge of a forest at dusk. You have been walking through it all day, and you have mapped most of what you have passed through. The trees, the streams, the clearings. You have a good map. You trust your map. But now at the edge of the forest you look out and see that the forest does not end here. It continues vast and darkening, in every direction, and the map in your hand covers only the smallest region of what lies ahead. And worse, now that you look at your map more carefully, now that you compare it with the features of the terrain at this edge where the familiar gives way to the unknown, you see that there are places where the map and the terrain do not quite agree. Small discrepancies, subtle mismatches, places where the map shows a clear path but the ground shows something else. And you realize that the map was not as accurate as you thought, not in the region you have already been through. And if it was not fully accurate there, in the terrain you could see and walk and measure, how accurate can it be in the vast dark forest ahead, the one you have never entered, the one your instruments cannot yet penetrate? This is roughly where science stands today, not lost, still holding a map, still able to navigate, still making progress in 1,000 specific questions and practical applications, but aware, in a way that is increasingly impossible to ignore, that the map is incomplete and in places misleading. Aware that the territory extends in directions the map does not represent. Aware that the very concepts the map is drawn in, space, time, matter, causality, observation, may be inadequate to describe the deeper terrain. And aware that the next breakthrough, when it comes, is unlikely to look like a minor correction. It is likely to look like a new map, drawn in a different language, organized by different principles, describing a territory that includes what we knew before, but reveals it to have been only one corner of something incomparably larger. And here is what that means for you. Sitting where you are right now in whatever light surrounds you, with whatever sounds are reaching you, with the immediate and undeniable weight of your own experience pressing on you from the inside, it means that the reality you feel you inhabit, the solid, colored, temporal, spatial, causally ordered world of your everyday experience, is, at some level, a representation. A useful, functional, evolutionarily honed, mathematically describable representation of something that does not, at its deepest level, look like that. The thing it is a representation of is what physicists and philosophers are trying to reach, and they are finding that every time they get closer, every time they peel back another layer, the thing underneath is stranger than what was above it. Not just different, stranger, more counterintuitive, less like the experience of a human being navigating a world, and more like something for which human intuition and human language were not designed. There is a word that physicists sometimes use in this context, emergence, and it is a word worth dwelling on, because it is doing enormous work in contemporary physics, and it carries within it a deeply philosophical claim. Emergence in physics refers to the appearance of properties or patterns at large scales that are not present in the underlying components and cannot be easily predicted from them. Temperature is an emergent property. It does not exist at the level of a single molecule, but emerges from the collective behavior of vast numbers of molecules. Life is an emergent property. It does not exist in any single atom of a living organism, but emerges from the organized interaction of those atoms. Consciousness, many scientists believe, is an emergent property of certain kinds of complex information processing systems. And now, in the frontier of theoretical physics, space and time themselves are being described as emergent, as patterns that appear at large scales from underlying processes that are not themselves spatial or temporal. If emergence is the organizing principle of reality, if the things that seem most fundamental and most real to us are in fact high-level collective patterns built on top of something entirely different, then what we have been calling reality is the surface of a very deep lake, and all of human experience, all of human science, all of human history has been conducted on that surface without any awareness of the depth below. The fish does not know it is in water. The human being does not know it is in emergence. The categories we use to think, space, time, object, cause, self, are the categories of the surface, not the categories of the depth, and using surface categories to investigate the depth is like trying to understand the ocean by studying only waves. The philosopher Thomas Nagel wrote a book called Mind and Cosmos in which he argued, controversially, that the standard neo-Darwinian picture of the world, a picture in which the universe is fundamentally physical, consciousness emerges from purely physical processes, and the appearance of mind in the universe is a late and accidental byproduct of blind evolutionary processes, is almost certainly false, not because of religious conviction or metaphysical preference, but because the existence of consciousness, the fact that there is subjective experience in the universe, seems so radically inexplicable on purely physical terms that it suggests the physical framework itself is incomplete. The universe must, in some sense that we do not yet understand, be hospitable to mind, and that hospitability must be a feature of its fundamental structure, not an accident of one planet's evolutionary history. If mind is not an accident, if consciousness is in some sense built into the structure of reality, then the picture of a purely objective, purely exterior, purely mechanistic universe that science has been building since the 17th century is missing something essential, something that is not on the outside of things but on the inside. This is a genuinely radical suggestion, and it is worth being clear that it remains deeply controversial and far from established. But it resonates with the wider pattern of this story, the pattern in which every layer of reality we have examined has turned out to be more complex, more strange, and more interconnected than the layer above it, the pattern in which the confident assumption of each era has turned out to be an approximation to something deeper and less familiar. And it raises a question that is perhaps the most profound and the most personal that this entire story has pointed toward. If consciousness is in some sense fundamental, if the inner dimension of experience is not reducible to physical processes, but is coextensive with them, or underlies them, or is in some sense prior to them, then what does that say about the relationship between the universe and the minds that observe it? Because there is something peculiar and almost unbearably suggestive about the fact that the universe produced through 14 billion years of physical and chemical and biological evolution, beings who can ask questions about the universe, beings who can build telescopes and accelerators and mathematical frameworks and use them to probe the structure of reality at scales ranging from the Planck length to the observable horizon. Beings whose brains contain in some sense a model of the universe, a representation of the whole within a part of the whole. There is something recursive, something self-referential, something that feels almost intentional about this, though we must be very careful not to let that feeling lead us into conclusions that the evidence does not support. But the self-referential character of a universe that contains beings who model the universe is not just poetic. It may be physically significant in ways we are only beginning to understand. Wheeler's participatory universe, the idea that observers are not passive recipients of a pre-existing reality, but active participants in bringing that reality into being, takes this self-reference seriously. In quantum mechanics, as we have seen, observation is not a passive act. The act of measurement collapses the wave function, selecting a definite outcome from a superposition of possibilities. If this is a fundamental feature of reality, rather than just a feature of our current formalism, then the universe cannot be fully described independently of the observers within it. The observers are not just looking at the universe, they are in some sense creating it or at least completing it, collapsing its quantum superpositions into definite facts through the act of looking. And if that is true, if observers play a constitutive role in the physical universe, then the picture of a universe that exists independently, fully formed and fully real, prior to and independent of any observation, is not correct. The universe is, in some sense, being made as it is being seen. This is not idealism in the traditional philosophical sense. Wheeler was not saying that the universe is a product of mind. He was saying something more subtle and more physical, that the quantum mechanical structure of reality is such that observation and reality are not cleanly separable, that the universe is a self-excited circuit in which observation and existence are mutually dependent. Whether this interpretation of quantum mechanics is correct is deeply contested, but the fact that it can even be seriously proposed, that a mainstream physicist working in the tradition of Einstein and Bohr could arrive at the conclusion that observers play a constitutive role in physical reality, tells you something about how far from the intuitive, Newtonian picture of an objective, observer-independent reality the physics has traveled. So let us arrive finally at the question that this entire journey has been circling. Not a technical question, not a question about the details of any particular theory, but the deep, personal, existential question that all of this forces upon you if you take it seriously. The question is simply this: what is real? Not in the sense of asking for a list of things that exist, but in the fundamental sense, what does it mean for something to be real? Is the solid world of your experience real? Yes, in the sense that it is consistent and functional, and you cannot pass your hand through the wall. But is it real in the sense of being what the universe actually is at its deepest level? The physics says no. Is the quantum world described by Schrödinger's equation real? It makes accurate predictions, but no one agrees on what it is describing. Is space-time real? Maybe emergent? Is consciousness real? Undeniably from the inside, the most undeniable thing in your experience, but inexplicable by the physics that describes everything else. Is the mathematical structure of physical law real? Or is it a description, a model, an approximation to something that the mathematics cannot fully capture? These questions do not have answers that science has currently established, and the honest position, the position that the evidence actually supports, is not confident silence. It is not quiet resolution. It is the acknowledgement that we are genuinely uncertain at the most fundamental level about the nature of what we are inside of. The universe exists. Something is going on. You are having an experience right now, an experience that feels entirely real from within, but the relationship between that experience and whatever is actually happening at the level of quantum fields and emergent spacetime and dark energy and the hard problem of consciousness, that relationship is not understood. The map is not the territory, and the gap between them may be larger, deeper, and more consequential than we have been willing to admit. In 1931, the mathematician Kurt Gödel published a proof that shook the foundations of mathematics with an impact similar to what quantum mechanics had done to physics. His incompleteness theorems showed that in any consistent mathematical system powerful enough to describe basic arithmetic, there will always be true statements that cannot be proven within that system. Not statements that are currently unproven, statements that are in principle unprovable, regardless of how much you extend the system or how clever you are. The system contains truths that it cannot reach, and to prove those truths, you need a stronger system. But that stronger system will itself contain truths it cannot reach. The hierarchy is infinite. There is no complete, consistent, closed mathematical framework that can prove everything true within it. Truth outruns proof, always and forever at every level. The implications of Gödel's theorem for physics are contested and subtle, but there is a resonance that is hard to dismiss entirely. Physics describes the universe using mathematical frameworks. If those frameworks are subject to Gödel's limitations, and there are serious arguments that they are, then there will be features of physical reality that the mathematical frameworks we use cannot describe or predict, not because of insufficient data or insufficient cleverness, but because of a fundamental logical limitation of formalized reasoning itself. The universe may contain truths that no mathematical theory can reach, features of reality that are real, that have physical consequences, that are in some sense present in the world, but that are beyond the reach of any formal description we could ever construct. This is perhaps the deepest form of the problem we have been circling. Not just that our current theories are incomplete, but that the very method we use to build theories, formal mathematical reasoning, may be constitutionally incapable of reaching the deepest level of the real. We have been mapping the universe with a ruler that is made of the same material as the thing we are measuring. We have been trying to describe reality with tools that are themselves features of reality, and those tools may have limits built into them. Limits that are not defects to be corrected, but structural features of all possible tools of this kind. If that is true, then the project of a complete description of reality, the project that has driven physics and mathematics and philosophy for centuries, may not be merely unfinished. It may be, in a deep and irrevocable sense, impossible. Not because reality is too complicated, but because description itself, the act of representing one thing in terms of another, has limitations that no amount of intelligence or effort can overcome. And yet, and this is the paradox that this story leaves you with, the paradox that has no resolution, you are still here. You still exist. You are still having an experience. The universe is still going on, doing whatever it is doing at the level of quantum fields and space-time geometry and dark energy and emergent consciousness, regardless of whether any description of it is complete or correct. The reality that underlies your experience is not diminished by the inadequacy of our theories about it. It does not become less real because our maps of it are wrong. Something is there. Something is happening. The question is only, and it is not a small only, what that something is. Scientists are not giving up. Let that be clear. The response to crisis in science is not despair, but deeper investigation, stranger proposals, more creative thinking. There are physicists today pursuing quantum gravity with the same passion and rigor that Newton brought to celestial mechanics and Einstein brought to the problem of electrodynamics and motion. There are neuroscientists probing the neural basis of consciousness with tools and frameworks that would have been unimaginable a generation ago. There are mathematicians developing new structures, category theory, topos theory, homotopy type theory, that may provide new conceptual languages for describing reality at levels where our current language breaks down. The work is ongoing, urgent, and in many ways more alive and more surprising than it has been in decades. The crisis is real, but it is a generative crisis, a crisis that is forcing new thinking, new connections, new questions that the old confidence would never have motivated. But the work being done now, however brilliant and however necessary, has not yet resolved the deep problems. The incompatibility of quantum mechanics and general relativity persists. The nature of dark matter and dark energy remains unknown. The measurement problem in quantum mechanics remains unsolved. The hard problem of consciousness remains intractable. The Hubble tension remains unexplained. The foundations of time, of space, of causality remain contested. And the possibility that some of these problems may not be solvable within the current conceptual framework, that they may require the kind of radical reconceptualization that happened in 1905 with special relativity, or in 1927 with the consolidation of quantum mechanics, remains very real and is taken seriously by many of the most thoughtful people in the field. What should you do with all of this? Not panic, not despair, not retreat into comforting certainties that the evidence does not support, but perhaps something harder and more important. Sit with the uncertainty. Let it be real. Let it be present, because the uncertainty is not a temporary inconvenience on the way to eventual understanding. It is right now the most accurate description of the situation. We are beings of finite cognition, equipped with senses shaped by evolution for survival rather than truth-seeking, using mathematical tools that may have inherent limitations, living inside a reality that our best theories describe as 95% unknown, trying to understand a universe that may be spatially infinite and that began in a moment our physics cannot describe, governed at its most fundamental level by laws that two of our greatest theories contradict each other about, producing as one of its most remarkable features the very consciousness that is trying to understand it, a consciousness that cannot step outside itself to check whether its understanding corresponds to what is actually there. The universe is not waiting to be understood. It is not holding its secrets patiently, confident that we will eventually arrive at the right answer. It is not a puzzle with a solution encoded somewhere in its structure that sufficiently clever mathematics will eventually decode. It may be something far stranger than a puzzle, something that exceeds the category of puzzle entirely, something for which the concepts we would need to understand it are not yet available and may never be available, not because they are too difficult to discover, but because they are too different from anything the human mind has yet produced. That is the edge we are standing at. That is the silence that is falling. And in that silence, ring in the space between what we thought we knew and what we are beginning to suspect, there is something that is not quite fear, and not quite wonder, and not quite awe, but partakes of all three. It is the feeling of a boundary dissolving, not the boundary between one theory and the next, not the boundary between one century's physics and the next, but something more fundamental, the boundary between the map and the territory, between the model and the reality, between the experience of the universe and the universe itself. That boundary has always been there, but we did not always see it, because the maps were good enough to make us forget they were maps. Now the maps are failing at their edges, and the territory is showing through, strange and vast and utterly indifferent to our categories, and the silence that falls in that moment of recognition is the sound of certainty dissolving into something that is neither knowledge nor ignorance but something in between, something that might be the beginning of a truer understanding, or might be the first glimpse of a depth that understanding can never fully reach. You began this journey in a place of implicit trust, trust in the solidity of the floor beneath you, trust in the laws that govern the matter you are made of, trust in the theories that describe the universe you inhabit. That trust was not naive. It was earned over centuries by some of the most brilliant human minds who have ever lived, through work of extraordinary rigor and care. The laws they discovered are real. The predictions they enabled are accurate. The technology they made possible works. None of that changes. But what changes, what this journey reveals, if you have followed it honestly, is the nature of what that trust was actually trusting. It was trusting the map. And the map, it turns out, is not the territory. The map is extraordinarily useful, extraordinarily precise in the regions it covers, extraordinarily well tested within its domain, but it does not cover everything. It does not reach the deepest level. It contains internal contradictions at its edges that point towards something beyond it that we cannot yet see. And the territory, the actual, fundamental, underlying reality that the map is trying to describe, remains, at its deepest level, unknown. So the next time you sit quietly and look at your hands, the hands you have looked at 1,000 times, the hands made of atoms, those atoms made of particles, those particles described by quantum fields that exist in a state of permanent quantum indeterminacy until the moment of measurement. The next time you consider that the space between those atoms is not empty, but filled with fields and virtual particles and quantum foam at scales too small to conceive, that the very solidity of your hands is an emergent property of quantum mechanical repulsion, rather than any classical impenetrability of matter, that the electrons orbiting the nuclei in those atoms are not following definite paths, but existing as probability distributions in space, that the atoms themselves are almost entirely empty space, that the forces holding those atoms together are mediated by the exchange of virtual particles that briefly borrow energy from the vacuum and pay it back before they can be detected, that the cells those atoms compose are themselves vast and complex as cities, that the proteins folding inside those cells are following rules that emerge from chemistry, which emerges from physics, which emerges from something deeper that we do not yet have a name for. The next time you look at your hands and try to hold all of that simultaneously in your mind, you may feel something shift, not dramatically, not catastrophically, but quietly and irrevocably, a small displacement of certainty, a hairline crack in the confidence that you know what you are looking at. That feeling, that quiet, persistent, irresolvable uncertainty, is not a failure of understanding. It is what understanding actually looks like when it is honest about its own limits. It is what you feel when you stop confusing the map for the territory. It is the specific texture of standing at the edge of what is known and looking out at what is not, with all your knowledge intact and all your certainty dissolved, in the peculiar and vertiginous awareness that the universe is vastly larger, deeper, stranger, and more mysterious than any theory has yet described, and that you, this consciousness, having this experience in this moment, are somehow inside it, somehow made of it, somehow capable of asking these questions about it without having any certain answer to the most fundamental question of all. What is it that you are inside of? What is this? What is any of this? And that question, the simplest, most ancient, most immediate question that a conscious being can ask about its own existence, remains after all of this, after all the centuries of science and mathematics and philosophy and experiment, after all the triumphs and revisions and revolutions and crises, after all the maps and all the territories. That question remains open, not because we haven't tried, not because we haven't been brilliant or rigorous or creative or dedicated, but because the question is genuinely hard, harder than we thought, harder perhaps than we can fully appreciate from inside the cognitive architecture with which we are equipped to think. The universe is not giving us a clean answer. It is giving us more questions, deeper questions, stranger questions, questions that dissolve the very frameworks in which they were asked, and reform in shapes we haven't yet learned to hold. And perhaps that is not a failure. Perhaps that is the most important thing science has ever told us. Not any specific discovery, not any specific law or theory or equation, but the deeper discovery that the universe is precisely the kind of place that resists final description, that retreats further from certainty the more carefully you look, that reveals greater strangeness at every deeper level, that seems, in its very structure, to exceed the capacity of any finite mind to fully comprehend. Perhaps the deepest truth that science has uncovered, in all its centuries of patient and rigorous investigation, is not a fact about particles or fields or the geometry of space-time, but a fact about the relationship between reality and understanding, that reality is always more than any understanding of it, that the map, however good, is always smaller than the territory, that certainty, however earned, is always provisional, that the moment you feel you have finally understood the universe is precisely the moment to look more carefully, because there, just beyond the edge of what you can see, something stranger is waiting. Scientists thought they understood reality, and in some ways, in many important, beautiful, useful ways, they were right. The laws they found are real. The predictions they made were confirmed. The universe they described is recognizably the universe we inhabit. But understanding something is not the same as understanding everything. And the difference between what we know and what there is to know, that difference, it turns out, is not a gap to be closed by more of the same effort. It is an abyss whose depth we have only recently begun to see, an abyss that may not have a bottom, an abyss that the universe is not hiding from us out of cruelty or indifference, but that opens naturally, inevitably, at the edge of every map, because that is what reality does. It exceeds description, always, at every scale, in every direction. It was never fully inside the equations. It was always more than the theory. It has always been, and remains, beyond the last page of every book ever written about it. Present, undeniable, immediate, and unknown.